This is Wendy Penn presenting the fifth lab report of Physics 2211 about the following slinky. The purpose of this lab is we choose our own model to analyze, and using tracker. So I chose the following slinky, and I try to use tracker to analyze the motion of a stretched slinky falling from rest, which is like the bottom of the slinky stays stationary until the top part all the way falls to the bottom. And use GlowScript to come up with a computational model and compare with the observed phenomena. So these are some important physical principles in this lab. Firstly, Newton's second law, which is dp over dt. In this lab, the net force is specifically equal to the sum of the gravitational force, which is negative mg in the y direction, drag force, which is negative b, times the magnitude of velocity squared in a v-hat direction, and b is the proportionality constant, and the slinky force, which is the tension force, it becomes an applied force once the gravitational force acts upon the top of the slinky. We'll also be using velocity update formula and position update formula, where Vf is equal to Vi plus Fnet over mass times delta t, and Rf is equal to Ri plus average velocity times delta t. And a preview to the results, which is the observed data and the computation model, pretty much align. So here's a screenshot of the tracker page. The mass of an average slinky is about 0.25 kilograms. The initial position I track is 4.44 times 10 to the negative 16th and 1.786 times 10 to the negative 2 meters. And the initial velocity, since it's starting from rest, it's 0, 0, 0. And then the frame rate is 1/30 frame per second. Here are the initial conditions. Plugging in the mass, position, and velocity from the last slide, the delta t is the size of each time step. Then we have the gravitational constant, 9.8, j hat pointing to the positive y-axis, and b constant is determined by trials and errors. And this is the first loop for when the bottom of the slinky stays motionless. The gravitational force and tension force have the same magnitude but pointing in the opposite direction, leading to a zero net force. The velocity and position update formula are used. This is the second loop, simulates the motion of the bottom of the slinky when it starts to move. Gravitational and drag forces act upon the bottom of the slinky. And again, velocity and position update formula are used. And as we compare the computational model and the observed data, the two graphs align pretty closely. The discrepancies occur when the bottom of the slinky starts to fall, which may be due to continued tension forces, as we only assume the slinky falls as one. Other parts of the slinky may continue to stretch out and collide with the bottom part, resulting in other forces changing the velocity and position of the bottom of the slinky. It may also be because of human errors when tracking the position of the bottom of the slinky.